For part C of the question, we're asked, what is the displacement of the ball from launch to landing? Well, we just said the vertical displacement of the ball from launch to landing is 0 vertically. So that means the overall displacement from launch to landing is purely in the horizontal direction. So we're going to be looking for this displacement here in the x direction. So for part C, that means we're really just interested in what's going on in the x direction for once. And since we already know the time it takes the ball to hit the ground once it's launched, we can use that information to help solve this problem in the x direction. So last time we said the time the ball was in the air was 5.9377 seconds to 3 significant figures. We also know the initial x velocity of the ball is 21.1603 meters per second. And in this direction, the x displacement is just equal to the constant velocity of the ball times the time it was in the air. So v1x was 21.1603 meters per second with 3 significant figures, and the time was 5.9377 seconds, also to 3 significant figures. So our displacement of the ball in the x direction will end up coming out to 125.643 meters, rounded to 3 significant figures. Therefore, the ball travels 126 meters horizontally. Actually, let me change that. We were given a direction. It wasn't just forward, it was east from launch to landing. And for part D, we're asked, what is the impact velocity of the ball? Now you could do this the easy way or the hard way. I'm going to do it the hard way to pretend that I don't see any symmetry in this problem. But if we look at our original sketch, it is a symmetric problem. So what that means is that the initial velocity vector, which is pointing in the x direction and the y direction upward, is going to be exactly the same at this point here, except now the y velocity is downward instead of upward. The x velocity is exactly the same, pointing forward in the x direction. But let's pretend I don't notice that yet. And so I'm going to do it using the kinematics equations. So in the y direction, now I'm going to be interested in what is the final velocity of the ball. In the x direction, it's still pretty straightforward. v1x is equal to v2x, which is constant in time, and we already found that was 21.1603 meters per second. In the y direction, we know the initial velocity of the ball, 29.1246 meters per second. We know the acceleration due to gravity, 9.81 meters per second squared down. From launch to landing, we know that the displacement in the vertical direction is 0. We don't know, let's say, we don't realize what the final y velocity is. So we take a look at those variables in the y direction and we realize that we can use this equation. In this equation, there's a simplification. This is just equal to 0. So what is this equation telling us? v2y is equal to plus or minus the square root of 29.1246 squared. In this case, we're interested in the landing y velocity. So we know that we don't really need this positive root. This root isn't admissible to us now. Therefore, v2y is negative 29.1246 meters per second. So what that's telling us is at the moment that the ball hits the ground, it's traveling forward in the x direction by 21.1603 meters per second, and it's going down in the y direction. I'll draw that vector a little bit longer. 29.1246 meters per second. Both of those are to 3 significant figures. and that's our angle theta. If we compare that to our original initial velocity vector, it's exactly the same triangle. This is 29.1246 meters per second up. This is 21.1603 meters per second east. But now we've just switched the direction. Therefore, actually I should change this. This should say V2. V2. V2 has to be 36 meters per second. And this time I didn't leave enough room for direction. It's going to be 54 degrees below the horizontal.